Okay. Hi, hey, hello, and happy 5.3, 5.4 quiz review. This is from the worksheet we did in class, or it should be on Players if you haven't looked at it. But I just wanted to go through some of them, all of them. All right, so our first question is using a sum or difference identity to find the exact value. Exact value means I'm not just going to punch it into a calculator. I want to find an exact value, probably using our unit circle. If I look at 11 pi over 12. A lot of people don't like radians, and I respect that. So if figuring out what two angles to add or subtract together in order to find the cosine feels a little bit difficult, we can always translate this into degrees by multiplying it by 180 over pi. I know the pi's are going to cancel out, so I have 11 times 180 over 12. I've already done the math for this one. I know it's going to be 165 degrees. From here, I get to decide what two angles am I going to add or subtract to get to 165 degrees. Personally, I said 135 and 30. I saw someone do 120 and 45. Anything is a-okay. Now, I get to look at what function I'm using. I see its cosine, and I'm told very specifically to use sum and difference. So I know that the cosine sum and difference is the cosine of A plus or minus B equals cosine of our first angle A times cosine of our second angle B minus or plus, because the signs flip-flop, the sine of A times the sine of B. Yeah, sine of B, there we go. So I can designate my 135 as my first angle A and my 30 degrees as my second angle B. And what's that going to get me? I'm going to have cosine of 135 degrees times the cosine of 30 degrees. Here I see I'm adding my two angles together. That means I'm going to be subtracting my values. I have sine of our first angle, 135 degrees, times sine of our other angle, 30 degrees. From here, we get to look at our unit circle and find exact values for these points. So the cosine of 135, or 3 pi over 4 if you like radians, is that negative radical 2 over 2. Cosine of 30 is radical 3 over 2. That minus sign tags along for the ride. Sine of 135 is going to be radical 2 over 2. And the cosine of 30 is 1/2. From here, I get to multiply and combine. So negative radical 2 times radical 3 is going to be a negative radical 6 over 4. And multiplying my other fraction, I'm going to have radical 2 over 4. I want to combine my two fractions, and I see that they already have common denominators. So I have negative radical 6 minus radical 2 all over 4 for the exact value of cosine of 11 pi over 12. All right, let's look at our second one. Now, I saw a lot of people get pretty freaked out with this one. Sine of negative 75 degrees. We like it because it's in degrees, but we don't like it as much because it's negative. Now, something that I did, which might have been making it more difficult, was I said negative 45 plus negative 30 degrees, and I worked with negative angles. It's a lot of extra work. But I saw someone in one of my classes say, hey, can't I just say it's 150 degrees, which is on our unit circle, minus 225 degrees, which is also on our unit circle, without even having to get into those negative angles. And you know what? I like that more than what I did. So I'm going to casually ignore my weird negative angle fun stuff. Okay, for the sine double angle identity, I know that, double angle, sum and difference, I know it's sine of two angles being added, the sine of our first angle times the cosine of our second. For the angles, I have plus or minus, and for sine, the signs stay the same. So I also have plus or minus here. Sine of our second angle times cosine of our first angle. All right, Over here, using that 150 and 225, I'm able to designate each of my angles as A and B or U and V, as we've been doing in class. That 150 is my first angle, A, and my 225 is my second angle, B. From there, I get to throw those angles into our sum and difference formula for sine. So I have the sine of our first angle, that's 150 degrees, times the cosine of our second angle, 225 degrees. Here I see I'm subtracting my angles, which means I'm also going to be subtracting my values, times the sine of our second angle, 225, times the cosine of our first angle, 150 degrees. All right, and from here, we get to look and utilize our unit circle to figure out what are our actual values. So I'm going to start with that 225 because it is one of my favorite angles because it's a variation of 45. I know that sine and cosine are going to have that same value of radical 2 or 2 over 2, but the signs, if it's positive or negative, are probably going to change. 225 is in our third quadrant, which means both of these are going to be negative, and that original subtraction sign between the two carries along for the ride. Now I get to look at the cosine of 150 degrees. 150 degrees, and I'm going to fix that. Remember the sine of 150 degrees. And the sine of 150 degrees is 1/2. The cosine of 150 degrees is negative radical 3 over 2. From here, I get to multiply straight across just like before. Get negative radical 2 over 4 minus, I have a negative radical 2 times a negative radical 3, which gives me a positive radical 6 over 4, but the subtraction sign is still there. So if I combine those two fractions, I get negative radical 2 minus radical 6 all over 4 as the exact answer for sine of negative 75 degrees. All right, I'll give you a second just to catch up, and then we'll move on to our next one. Okay. All right, this is using our double angle identities. So our second one, given that sine of theta is 7/10 and theta is in quadrant 2, we want to find the double angle values for each of our trig functions. My first step is draw a triangle. I know that I have the sine of theta over. I know that I have the sine of theta. However, the fact that I'm in the second quadrant tells me a few things. Mostly, it tells me what orientation should I draw my triangle and what sides are going to be negative or positive. From here, I have at theta, sine is 7/10. I'm able to utilize the Pythagorean theorem to get square root of 51 as our last side. Now, since we're in the quadrant 2, that's telling me that our x values are going to be negative. So that radical 51 is going to be a negative radical 51. All right. Now, let's look at sine of 2 theta. My normal first step is to write out what identity I'm using, because it helps me out. The sine of 2 theta has a double identity equal to 2 times the sine of theta times the cosine of theta. How that translates is the 2 is just staying along for the ride and multiplying by everything else. I don't know what theta is, but I know from using my triangle that the sine of theta is that 7 over 10. I also know that from the question, it was given to us. That opposite over hypotenuse. And also using our triangle, and since I have that last side now, I know that our cosine is that adjacent over hypotenuse, or that negative 51 over 10. From here, I just get to multiply my fractions. And a lot of people get freaked out because that 2 is in a fraction, but we know that we can put any whole number over an invisible 1 to help us remember what fraction multiplication is going to look like. I know that for fraction multiplication, the numerators and denominators both multiply straight across, so that 2 times 7 times negative radical 51 is going to get me negative 14 radical 51. In the denominator are 1 times 10 times 10 is going to get us 100. I'm not quite satiated because I see that I have negative 14 over 100, and I know that that can be reduced. So our final and most reduced answer is negative 7 radical 51, because it's under a radical, and I really can't do anything with it, over 50. All right. And so that was our sine. For cosine, if you remember, I have 3 different variations of our double angle identity that I'm able to work with. My personal favorite is using cosine squared minus sine squared. But just a reminder that I could also use 1 minus 2 sine squared or 2 cosine squared minus 1. They're all equal. I do have my favorite, however. And that's probably going to be the one that I'm working with. So in our first double angle identity, that cosine squared minus sine squared, my first step is to utilize that triangle I made. And remember that we said, okay, cosine is adjacent over hypotenuse, so that negative radical 51 over 10. And since it's our cosine value being squared, that's all being squared as well. Same thing with our sine. We said sine was 7 over 10. It's still being squared with the subtraction sign in between them. All right, here's where we get into some of our squaring rules. If I'm squaring a fraction, that means that the exponent distributes to the numerator and denominator. So negative radical 51 squared. Now I know a negative times a negative is a positive, and squaring is the opposite of taking a square root. So if I square a square root, I have whatever is underneath it. So I'm left with a positive 51 in the numerator. 10 squared is still just 100. That subtraction sign is just coming along. 7 squared is going to be 49 over that 10 squared, 100. They already have a common denominator, which is very convenient for me. 51 minus 49 is 2 over our common denominator of 100. I'm still not super satiated because I know that that can be reduced, and it absolutely should be, to 1 over 50. All right. And that is what we have for our cosine of 2 theta. I'm going to give you a second to catch up and copy this. You can pause if you'd like, because I'm going to need some space for that tangent of 2 theta. All right. Unfortunately, I'm going to erase most of what I've done so far, just so I can utilize some space. Okay, so tangent of 2 theta. My sum and difference identity for this is that it's 2 times the tangent of theta over 1 minus tangent squared theta. If I utilize that triangle I made, and I know that for tangent it's opposite over adjacent, I know that my tangent of that angle theta is 7 over negative radical 51, which means that I can bump that negative up into the numerator. I have a choice. I can rationalize it now, or I can leave it to rationalize later. I'm probably going to leave it to rationalize for later because I want to make things as simple as I can. But now that I know my value of sine of tangent of theta, I'm able to start plugging it into that double angle identity. So I have that 2 times the tangent of theta, 7 over radical 51, over 1 minus tangent squared, so that negative 7 over radical 51, now being squared. I'm going to clean this up a little bit. I can multiply that negative 2 in my numerator, so that my new numerator is negative 14 over radical 51. And I'm going to clean up my denominator by squaring it to get a positive 49 over 51. I see that I still have 1 being subtracting from that 49 over 51. So for the moment, I'm going to rewrite that 1 as a 51 over 51 so I can have common denominators and be able to manipulate it. From here, I'm going to, I'll do that step first. Negative 14 over radical 51. I haven't touched my numerator yet. 51 minus 49 is 2. I have 2 over 51. But I have a fraction over a fraction, which means that I'm going to be able to do that multiplying by the reciprocal of the denominator. So my numerator, that negative 14 over radical 51, stays the same. And I multiply by the reciprocal of the denominator. Our denominator is 2 over 51. Reciprocal makes it 51 over 2. All right. So this was a lot, right? I see that I have a 2 in the numerator and denominator. So that 2 in my denominator becomes a 1. I have 2 times 7 in my numerator, so I'm going to rewrite that. Now I have negative 7 times 51 over the square root of 51. All right. I believe that 7 times 51 is negative 357 over radical 51. But I'm not done yet, because I have a radical in the denominator, and I absolutely do not like that. We know from Mr. Poland's videos, as well as some of mine or in class, rationalizing the denominator, I multiply by my radical over my radical. So I would get negative 357 radical 51 over 51. And I will tell you that that negative 357 over 51 will reduce. So my absolute final answer is going to be negative 7 radical 51 for my tangent of 2 times my angle theta. All right, I'll give you just half a second to write that down, pause, catch up, etc. There we go. Okay, let's check out 3. Rewrite as the sine or cosine of a single angle. This is when I see that I have both sum and difference as well as double angle formulas. If we remember, our first step would be to analyze our expression and figure out what's happening. I see for the first term, our A expression, cosine 3b times cosine of 5b minus sine of 3b times sine of 5b. That looks to me like one of our sum and difference formulas, because I have all of our functions being multiplied out, and I also see that I have 2 different angle values, 3b and 5b. When I am analyzing our expression to figure out which of our sum and difference identities, I see that I have cosine of our 2 different angles being multiplied together. That is a big clue that I am using my cosine identity. If I'm using our cosine identity, then I'm able to look at the sign that is separating our 2 values. I know that for sine, the signs flip-flop, so if I'm subtracting my values, that means I'm adding my angles. From here, I get to fill it in. We've said cosine. I know that my 2 angles are 3b and 5b, and we just found out that we are adding those angles. So cosine of 3b plus 5b, I can absolutely simplify that, so I absolutely should, and get the cosine of 8b as our rewriting of our long expression into a smaller expression. All right, looking at that second one, 2 cosine squared 4b minus 1. That to me looks like it's the setup of a double angle identity, because I have one of my trig functions being squared with a 1 being tacked on. Definitely doesn't seem like sum or difference to me. Now I can analyze it and look to see, would it be sine, would it be cosine double angle? That general form of 2 cosine squared of some angle minus 1 is a absolute sure sign that we are using the cosine double angle identity. So I know that I'm going to be using cosine, and I know that whatever angle I have here, my 4b, when I put it into my double angle identity, I take half of it, which is telling me that for my building it back up, working backwards and rewriting it, it's going to be 2 times that 4b. I can absolutely simplify that, so I absolutely should. 2 cosine of 2 times 4 is 8b as our rewrite. All right, and looking at that last one, this one looks like a sum and difference one to me, because I have all of my trig functions being multiplied and then taking the difference of them. I look at one of my expressions, sine g times cosine h. If I have a sine being multiplied times a cosine, that's a sure sign that I'm working with a sine function, specifically a sine sum and difference. I see my two angles are g and h. Now I look to see what is the sine. I'm subtracting my values, and I know that for sine, the signs stay the same, which is telling me that I'm still subtracting my angles. Now, g and h have no terms in common. They're variables. I have to keep them apart. This is as simplified as I can make it. So we're going to look right here. I'll give you just a second to catch up, pause, etc. And that's fine. One day I'll learn how to erase these boards. Okay. All right. Okay. Now we're on 4. Evaluate without using a calculator. Now the wording of that prompt, problem, question is telling me that I'm going to have some sort of exact answer. Because evaluating, I know, is very similar to solving, but I'm not solving for a variable. I look and see, and I see that for that first one, it has the form of a double angle identity. I, from there, know that originally it's 1 minus 2, it's supposed to be a 2 up here, sine squared of some angle, and that is a cosine double identity. So if that is our format, and that pi over 2 is our new theta, I'm able to throw that back into our double angle original identity and say, okay, well, that's really equal to cosine times 2 pi over 12. And what is the cosine of 2 pi over 12? Well, immediately I probably don't know, but 2 times pi over 12 is pi over 6. And pi over 6 is absolutely on our unit circle, and the cosine of that value of that angle is radical 3 over 2, and that is the exact value of 1 minus 2 sine squared of pi over 12. All right, let's look at that last one. This one makes me pause for a second, because I'm not used to seeing a 10 out in front. I know that it kind of looks like my sine double angle identity, where I have 2 sine of a theta times cosine of a theta, but now I have a 5 being multiplied in the front. We are able to factor that out and leave that 5 out for the time being and come back to get it. I see that for this one, our theta is at 75 degrees, and I know that that 2 sine theta cosine theta is equivalent to the sine of 2 theta. So my exact example is equivalent to sine 2 times 75 degrees, except I said that I couldn't forget about that 5. It's still just being multiplied in front, because all of this, that 2 sine theta cosine theta, is equivalent to our sine 2, in this case, 75. But we need to multiply that 5 out in front. 2 times 75 is 150. And that 5 is still just coming along for the ride. I can look on our unit circle and figure out when our angle is 150 degrees, what is the sine of that angle? And it happens to be 1/2. But that 5 is still being multiplied. So 5 times 1/2 is going to be 5 halves, or what is it, 2.5? The only decimal that I will accept. All right, I'll give you just one last second to check it out, pause, etc. And I'll try and erase for real this time. Cool. All right, last one. If you're working on the worksheet we saw in class, or maybe the one on Polaris, you will see that I have one less of our identities here than I did on the worksheet. That's because that 1 minus tangent squared x equals cosine of 2x over cosine squared x is gone. Don't worry about it. We're not doing proving with double identities, double angle identities. But I'm still going to try and work with this one. Similar to before, I'm going to box in my right-hand side. and I'm going to work on proving that. Sine of x minus pi over 2 equals negative cosine of x. On my left, it looks like I'm utilizing a sum and difference identity. I have the sine, a trig function of two angles that are being added or subtracted, so I'm going to denote them as my u and v. From there, I'm able to throw each of those angles into my sum and difference identity for sine. So sine of the first angle times cosine of that second angle, pi over 2. Here I'm subtracting my values, which means I'm subtracting my values over here as well, times sine of our second angle times cosine of our first angle. Now x is not an angle on our unit circle, so at the moment that sine x and cosine x can't do anything but just keep tagging along for the ride. Cosine of pi over 2, using our unit circle, I know is 0. Anything times 0 is also 0, so that sine x times 0 goes away. However, that negative sign is still there. I can't forget about it, even though the other half of it is 0. Sine at pi over 2 is 1, so I have negative minus 1 times cosine, which is really negative 1 times cosine, aka negative cosine, and my left matches my right in a proof that's way, way easier than what we did in 5.2. And let's look at that other one. It looks like I have two sum and difference identities and they're both using cosine. So just like before, I'm going to mark them with a u and v. And I'm going to start with the one on the left. So cosine of our first angle times cosine of our second angle. Here I'm subtracting my values, which means that here I am adding them. Sine of our first angle times sine of our second angle. And that is our first half. Now I have to deal with that cosine of x plus y. Same thing as before. I have cosine of our first angle times cosine of our second angle. Here I'm adding my angles, which means I'm subtracting my values. Sine of our first angle times sine of our second angle. And I'm noticing a few things. I see that I have plus sine x sine y, and I have minus sine x sine y. Anything minus itself subtracts out to 0, so I lose both of these terms. The other thing that I'm seeing is I have cosine x, cosine y, cosine x, cosine y. They're the same term. They are able to be added. Before I had two separate ones. Now they are together as 2 cosine x, cosine y. Proofs that are much, much easier than 5.2. And just another reminder that you do not have to know how to do any of the proofs utilizing double angle identities, although you do still have to use double angle identities for this quiz. All right, that is a nice walkthrough of the review that was posted on Polaris and or done in class. Hope that helps. If you have any questions, feel free to email Mr. Pullen or I, and have a great day.